Is about instruction set of 8086 microprocessor. Now, what is an instruction? Instruction is a command given to the processor by the user to perform a specific task. And what is the format of an instruction? Instruction internally contains an opcode along with operands. Now, opcode specifies the type of operation to be performed by the processor on the given operands. Okay. Now, let us see the instructions which are supported by 8086 microprocessor. Now, these are the instructions which are supported by 8086. As you can see, data transfer instructions, arithmetic instructions, logical instructions, shift and rotate instructions, flag control instructions, string instructions, branch instructions, and then machine control instructions. Okay. Now, initially we'll start our discussion with data transfer instructions. Now, the first data transfer instruction is move. So, move is a mnemonic, or move is an opcode which is given to the processor and telling the processor to do a specific task. Okay. Now, here move is a instruction. Okay, and here the meaning is move. Now, the format is move d comma s, or I can say it as a syntax, move d comma s. Now, s indicates source and d indicates destination. Now, what happens if this instruction is executed? Now, the contents of source gets copied into destination. Okay, contents of source copied into destinations, and none of the flags are going to be affected. Now, let us see the possible or allowed source and destinations. Okay, now here source can be of accumulator and destination can be of memory. So, you can perform a move operation between accumulator and a memory, memory and accumulator, register and register, memory to register, register to memory, and then immediate value to register. Okay, but we cannot go with these kind of operands. Like memory to memory is not possible, memory to memory transaction is not possible in case of 8086 microprocessor, and immediate to segment register, we cannot initialize a segment register with an immediate value, and we cannot copy a segment register into the other segment register. So these are not the operands which we should not use in case of this move instruction. Now, as you can see, one of the example, move AL comma BL. So I'm copying the content of this BL into AL register. Okay, this is the possible combination which we have used now, move AL comma BL, register and a register. Now, you can also use in the same way something like memory and accumulator. Now, here you can use something like move inside the brackets one address comma and then accumulator. Okay, and you can also use this combination like move some AX comma 1 2 3 4. Okay, so in this way you can use this move instruction. Now, move is the instruction which is used for copying the source content into destination. Now, we have the next instruction, that is exchange. XCHG is nothing but exchange. Okay, now what it does, it swaps the content between D and S, that is destination and a source. Okay, now the allowed operands inside this destination and source are a 16-bit register, accumulator, that is both can be exchanged, and register and a memory, register and a register, memory and a register. Okay, now we cannot perform an exchange operation between the memories and between the segment registers. Okay, now you can see one example here, exchange brackets 1 2 3 4 H comma BX. Now, what happens after execution of this instruction? Now, whatever the content that is present in this 1 2 3 4 location gets copied into BX, and the contents of BX gets copied into 1 2 3 4 location. So it performs exchange operation between this memory location and a BX. Now, let us see the load effective address and then data segment as well as extra segment instructions. Now, these three instructions are mainly used for loading the effective address into a specific register. Okay, so load effective address, LEA is nothing but, and then LEA register 16, which is nothing but 16-bit register comma effective address. So we have to give one effective address here. Now, what happens after execution of this instruction? Now, this effective address will be stored inside this 16-bit register, and if you are using this instruction, now this instruction not only loads one 16-bit register, that is a specified 16-bit register, but also loads the data segment register. Okay, as you can see here, the address which we are specifying here, that gets loaded into 16-bit register, as well as the address plus 2 will be loaded onto or will be loaded into data segment register. Okay, and this is similar, but it loads the data onto data extra segment, not to data segment. Okay, now here LEA SI data is similar to move SI comma offset data. Okay, now we have one more, that is XLAT, which is nothing but a translate instruction. Now what it does, it copies the contents pointed by this physical address location to AL register. Okay, now whatever the address that is pointing by this physical address location will be copied into AL register, and none of the flags are going to be affected. Now we have arithmetic instructions under this add, ADC, increment, AAA and DA. As we know what is addition operation, so here the syntax is add D comma S. So it performs addition between source and destination, and the result is again copied into the destination register. Okay, and if at all we get any kind of carry, now that carry will be stored inside this carry flag. Okay, now all the flags are going to be affected. That depends on the result that we got from this addition operation. Okay, and ADC is used for add with carry. Okay, for example, if we are performing, as this is an 16-bit microprocessor, if we want to perform 32-bit operations like addition between two 32-bit operands, then we have to use this ADC. Why? Because whatever the result or whatever the carry that is coming out of the lower word, okay, that should be added to the higher word addition. So in those cases we would be using this ADC. Okay, so ADC D comma S, which performs addition operation between source, destination as well as the carry flag, and the result is stored inside the destination register. Okay, and if you get any carry, now that carry gets copied into carry flag. Now all the flags will be affected. That depends on the result which we got. Now we have increment. Now it increments the destination by 1. Okay, so D plus 1, and the result is again stored into the destination operand. Okay, now all the flags are affected except the carry flag. Now we have AAA, which is nothing but ASCII adjust after addition. Now this is used in case of addition between two ASCII operands. Okay, if the sum is greater than 9, now the value in AH will be incremented by 1. And DAA, decimal adjust after addition. Now this is used in case of BCD addition. Now if you are performing any operation between two BCD operands, and if you got an invalid BCD result, then that should be added with a correction factor 6. Now that correction factor will be added by this DAA instruction. Okay, now let us see some examples. Add AX comma 2, it performs addition between AX and 2, and result is again stored into AX. ADC AX comma 2, it performs addition between AX, 2 and a carry flag, result is again stored inside this AX register. Now we have increment BX, now it increments the BX register by 1, and increment word pointer of BX, now it again gets increments the pointer BX. Okay, now we have one more example which shows for BCD addition. AL has 25 and BL has 56. Now we are performing addition between AL and BL. Now the result is again stored inside this AL. Why? Because DAA and AAA instructions will directly perform operation on AL register. Okay, so that is why these instructions are also called as implicit instructions, or this AL is also called as implicit operand for DAA and AAA. Okay, now after performing the addition between 25 and 56, we get the result as 7B. Okay, now whereas here 7 is a valid BCD, but B is not a valid BCD. Okay, BCD numbers are from, or we can represent decimal numbers by using this BCD from 0 to 9. Okay, anything more than 9 will not be considered as a valid BCD. So here B is not a valid BCD. So now this will be added with 6. Why? Because we are using now DAA instruction. Okay, so whenever this instruction is executed, 6 will be added to the result which is present in AL register. Therefore, we'll get the result as 81, which is a valid BCD result. Now we have subtract instruction. Now it does subtraction between the destination and source. That is, source is subtracted from the destination, and result is again stored inside this D. So if you are taking any borrow, then that will be present inside this carry flag. Okay, subtract with borrow, which is again similar to ADC, but it performs the subtraction between destination, source and a carry flag. Okay, and then decrement. Now it decrements the destination operand by 1, and again the result will be stored inside the destination operand. Now negation, it performs a ones complement operation on the destination, and again the result will be stored inside the destination. And DAS and AAS. DAS is similar to decimal adjust after addition, and AAS similar to ASCII adjust after addition. Now we have multiplication and division instructions. Mul is an instruction which performs the multiplication operation, and here we have mul s. Okay, the syntax is only mul s. It performs multiplication between the source operand and the destination operand. Now what is the destination operand? Now the destination operand is accumulator register. Okay, it performs multiplication between AL and specified source. Okay, and the result is stored inside this AX in case of 8-bit. Okay, if it is a word size, that is AX gets multiplied with 16-bit source, and the result is stored inside DX and AX. Okay, and division operation, again here it does the division between AX and the specific source operand. Okay, so divide S, source operand. So it performs the division of AX by this specified source operand. If it is an 8-bit operand, then AX gets divided by S8, and quotient will be stored inside AL, and remainder will be stored inside AH. Okay, if it is a 16-bit operand, then DX AX will be divided by this 16-bit register, and then quotient will be stored inside AX, and remainder will be stored inside DX. Okay, and IMUL and IDIV, these are the two instructions which perform signed operations. Okay, AAM, which is nothing but ASCII adjust after multiplication, and AAD, which is nothing but ASCII adjust after division. CBW, convert by 2 word. Now whenever this instruction is executed, then the sign bit of AL will be copied into all the bits of AH. Okay, MSB of AL will be copied into all the bits of AH. Okay, convert word to double word, which is nothing but here the MSB of AX gets copied into all the bits of DX. Okay, now here the source can be of register, 8-bit register or 16-bit register, 8-bit memory location or else a 16-bit memory location. Let us see. Now if you are performing a multiplication between 2 bytes, then the multiplicand should be AL, and we have to specify either a register or else a memory, or else a memory location. Now this register or memory will be multiplied with AL, and the result will be stored inside AX. Okay, and if you are doing multiplication between 2 words, that is AX and a 16-bit or 16-bit memory location, then the result will be stored inside DX and AX. So that is what DX is called as extended accumulator. Okay, now if you are performing division between word, then AX is the dividend, and divisor is register or memory, and AL and AH. AL stores quotient and AH stores remainder. And if you are doing double word or word, then DX and AX will be the dividend, and the divisor would be register or memory location, and quotient would be stored inside AX, and remainder will be stored inside DX. Now let us see some examples here. Assuming that each instruction starts from these values, AL is of 85H, BL is of 35H, and AH is 0H. Now we are doing multiplication. So mul BL, what it does here, it performs multiplication between this register. As it is a 8-bit register, it gets multiplied with AL. Okay, now it is multiplied with AL into BL. Okay, that is 85H into 35H. Now we have got one result. Now that result is a 16-bit result. Now that is stored inside AX register. Okay, and here we are doing IMUL, which is nothing but signed multiplication, that is between AL and BL. Now it initially converts AL into 2's complement form, and now that 2's complement form will be multiplied with BL. Now the result is again converted into 2's complement form, and that will be stored inside AX register. Okay, now we have division. So whenever this instruction is executed, div BL, it performs or else it divides AX by BL. Okay, as you can see, AX contains 85, that gets divided by 35, so we have got a result of 2. Okay, now 2 is stored inside this AL, and AH would be storing 1B. Now what is this 1B? 1B is nothing but remainder, and 02 here is nothing but quotient. Now let us see the logical instructions. Logical instructions are of 4 types here: AND, OR, XOR, and a NOT. So these instructions would be doing the basic operations like AND gate, OR gate, XOR gate, and a NOT gate. So what is the syntax for this AND? AND destination comma source. So it performs the AND operation between source and destination, and the result will be stored inside D. Now what is this AND operation? If any of the bit inside this operands are 0, then the result would be 0. Okay, if both the operands are 1, then only the result would be 1. So the same operation that is carried out by an AND gate will be performed by this instruction. Now we have OR. Now OR comma OR destination comma source. So it performs source plus destination, and the result will be stored inside the destination operand. Okay, if any of the operand is 1, it means if any of the operand bit contains 1, then the result would be 1. Okay, now we have XOR. It performs exclusive OR operation between source and destination, and the result will be stored inside the destination. Now what is this XOR operation? If 2 bits of the operand are same, then the output would be 0. If 2 bits of the operands are dissimilar, then the output would be 1. Okay, and NOT, it performs its operation on the destination operand, only one operand, and the result is again stored on the into the destination operand. As you can see, it is performing a negation, which is nothing but ones complement operation. So ones will be reversed to 0, and zeros will be reversed to 1. Okay, and the allowed destination and source operands for AND, OR, and XOR are shown here. So we can perform these operations on register, that is register to register, and memory to register, register to memory, immediate to register, immediate to memory, and then immediate to accumulator. Okay, and the allowed destinations for NOT operation or NOT instruction is register and memory, but it is not a immediate value. Now let us see some examples here. Uses any addressing mode except memory to memory and segment registers, especially used in clearing certain bits. Okay, this AND or AND instruction will be used for clearing some bits. Okay, so here we have an operand which is not specified, like it might be of any bit values. Now we have one more operand, as these bits are 0. Okay, irrespective of these bits, this higher nibble, okay, the result would be 0. Okay, and here as these bits are 1s, irrespective of these bits, that is the lower nibble, the result would be X. Okay, now in the same way, used in setting certain bits. Okay, so here it does the plus operation, that is addition. So as these bits are 0, irrespective of these bits, okay, or else whatever might be these bits, so the same bits would be appearing at the output. Okay, now as these bits are 1, irrespective of these bits, the outputs would be again 1. Now we have XOR. XOR, as I told you, that if 2 bits are same, then the output would be 0, and if 2 bits are dissimilar, then the output would be 1. Now we have shift and rotate instructions. There are totally 7 shift and rotate instructions, like shift right, shift arithmetic left, and then shift right, shift arithmetic right, rotate left, rotate right, rotate left through carry, and rotate right through carry. Let us see each and every instruction. Before that, let us see what is this logical shift and arithmetic shift. Now what is this logical shift? So if we are performing any left or right shift operation, okay, assuming that we are performing a right shift operation, now here the bit positions or the values present in the bits will be shifted towards right, and the vacated bit position on the MSB or on the LSB in case of a shift left will be appended with zeros, or will be added with zeros. Okay, now in case of logical shift, so shifting operation is carried out, but the vacated bit will be filled with 0. In case of arithmetic shifts, here the MSB is preserved. MSB is preserved, and it carries on the shifting operation. Okay, so here as you can see, MSB is preserved here, and again it is carrying out the shifting operation towards the right side. Okay, and this LSB is copied into the carry flag. Okay, and the same thing happens over here. LSB is again copied into the carry flag. Instructions. Now these are the shift instructions that we have, or which is supported by 8086 microprocessor. SAL, which is nothing but shift left or shift left arithmetic, and SHL is shift left. Now both performs the same. Why? Because here shift left will be shifting towards left, and the same thing is performed by this shift arithmetic left. Okay, now here the syntax is shift left destination comma count. Now if you want to shift this destination operand by 1 or by 1 time, then you have to specify this with a immediate value. Okay, if you want to shift this destination operand more than 1 time, then you have to specify the count register. So initially we have to initialize the count register with some value or with the specific shift value, and that should be specified here. Okay, now in the same way, shift right destination comma count. If it is 1 time shift right, then you have to go with the immediate value. If it is that means if you want to shift this destination operand by more than 1 time, then you have to specify the count register, that is CL register, and it should be stored with the specific count that you want to shift this destination operand. Okay, and in the same way, shift arithmetic right, syntax is same, SAR D comma count. Now here the allowed operands destination is register and the count should be 1. If destination is register, and if you want to shift this destination more than 1 time, then you have to use CL. Okay, and if the destination is memory and you want to use or you want to move the content inside this memory by 1 time, then the count should be an immediate value 1. Okay, if you want to move the content inside this memory by more than 1 time, then you have to go with CL register. Okay, so this is how the operation goes on. Shift left, where the data is appended towards the right side and data is shifted towards left. Okay, and the data which is shifted or the bit which is shifted from the MSB will be copied into the carry flag or will be moved on to the carry flag. Okay, shift arithmetic right, again it performs similar operation to shift left. Okay, shift right, now what happens here is the content inside this register or memory location will be shifted towards right side, and the LSB will be moved into carry flag, and the vacated positions on the MSB side will be appended or will be filled up with zeros. Okay, and shift arithmetic right, where the MSB is preserved initially. Okay, and from there it carries out the shift right operation. Okay, now as you can see here, shift left instruction performs a logical left shift. Okay, so it performing a logical left shift, and this MSB will be moved on to the carry flag. Okay, and what would be the allowed operands? So register and immediate, as we have seen. So memory and immediate, register and CL, and memory and some count value. Okay, let us see an example here. So shift left AX comma 1. So you are shifting the content inside AX by 1 time, and then you are copying that AX content into BX, and then you are initializing this CL with 2, and again you are shifting this AX by 2 times. Okay, and you are adding AX with BX. Now what happens here, whenever you shift something by left side, okay, so shift left n bits multiplies the operand by 2 power n. Okay, so if you are shifting one operand by 3 bits, so the operand will be multiplied by 2 power 3, which is nothing but 8. Now you have shift right instruction. It performs the shift right operation where the LSB gets copied into, or LSB will be moved into the carry flag. Now shift right n bits divides the operand by 2 power n. Okay, so here left shift will does the multiplication operation, but whereas right shift will be doing the division operation. Now shift arithmetic right. Now as we know that it preserves the MSB and then carries out the shift right operation where the LSB will be moved into carry flag. As you can see one of the example here. So we are performing SAR on DL. Okay, and we have got minus 40, and if you are performing it by 2 times, then we get minus 10. Now these are the rotate instructions: rotate left, rotate right, rotate left through carry, and then rotate right through carry. Okay, what do you mean by rotate? So rotate here is nothing but, if it is a rotate left, okay, now whatever the content that is moved out of the MSB, okay, shift operation takes place up to MSB, and the MSB will be copied into LSB as well as the carry flag in case of this rotate left operation. Okay, and the syntax is similar to the shift operation. So rotate right, again it is similar to the shift, but what happens here is the LSB will be copied into CF or will be moved into CF, and the same CF or same LSB will be copied into the MSB. Okay, now rotate left through carry. Let us see this with the picture. Okay, so rotate left instruction, as you can see that this MSB is moved on to the carry flag, and then the same MSB will be copied into the LSB. Okay, and if you go for rotate right instruction, it performs shift operation up to this MSB or up to this LSB, and this LSB will be moved into this carry flag, and the same LSB gets copied into the MSB. Now here rotate left through carry, what happens here is it performs the shift similar operation, but this MSB will be moved into carry flag, and the content of this carry flag will be moved on to the LSB. Now rotate right through carry, here it does the same. Here this LSB will be moved into the carry flag, and this carry flag content gets copied into or will be moved into the MSB. Now rotate instructions, same or similar to the shift. Now we have flag control instructions, okay, which would be performing the operations on the flags. CLC, it will clear the carry flag. STC sets the carry flag, and then CMC complements the carry flag. CLD clears the direction flag. STD sets the direction flag, and then CLI clears the interrupt flag. Now we have a compare instruction. Now it performs the comparison operation between D and S, that is source and destination. But what is that comparison operation internally? It performs subtraction between D and S, that is S is subtracted from the D. Okay, now the result will not be stored in any of these operands, but the result is going to affect these flags. Okay, so if D equal to S, assuming that both destination and source are equal, then ZF will become 0. Okay, and if D is greater than S, then ZF will become 0 and CF will become 0. And if D is less than S, then ZF will become 0 and carry flag will become 1. Why? Because we are subtracting this S from D, and the allowed destination and source operands are register to register, memory to register, register to memory, immediate to register, and immediate to memory, and immediate to accumulator register. Now we have string operations. Now what do you mean by string? String is nothing but array of bytes or words which are stored inside the memory. Okay, now what do you mean by a byte? As we know that 8 bits and word is nothing but a 16 bit. Okay, so if we are storing a sequence of or a collection of some elements inside the sequential locations of the memory, then those elements will be considered as a string. Okay, now the strings are going to support these instructions: copy, search, store, and then a compare. Copy is nothing but move or load, and search is nothing but a scan. Let us see that. So in case of string instructions, source will be considered as DSSI. Okay, so source location will be considered as the location which is pointed by this DS and SI. Okay, so we'll get, by adding these two registers, we'll get the physical address, and destination will be considered as ES and DI. Okay, now here direction flag. Now here we have to use this direction flag. If this direction flag is 0, if it is initialized to 0, then it means we are using auto increment mode. It means the memory locations or the memory will be incremented by 1 for every operation. Okay, and if you are using or if you are initializing this direction flag to 1, it means we are going with auto decrement mode, where the memory, the address will be decremented by 1 for every operation. Okay, so CLD is used for clearing the direction flag, and STD is used for setting the direction flag. Now let us see the instructions which are supported by this move instructions. Okay, so these are called as a prefix instructions: repeat, repeat E, and repeat 0, and repeat non-equal, and then repeat non-zero. Okay, prefix instructions, these instructions should only be used with these instructions, as you can see here. So repeat should be only used with move S and store S. Okay, So here this repeat instruction would be performing or would be executing these instructions until Cx becomes 0. Okay, and repeat equals and repeat Z should be used only with compare s and then a scan s. Okay, s is nothing but here string. Okay, and it repeats these instructions until Cx is not equal to 0 and Zf is equals to 1. Okay, if any of the condition fails, then it will not execute these instructions. Okay, and this instruction will be executing this instruction until Cx is again not equal to 0 and Zf should be 0. Now let us see those string instructions. Now here the first instruction is move s. Now move is, as we have seen, move on 2 operands. Now here this move is performed on 2 strings. Okay, that is between source and destination. As we know what is source here, that is ds plus si, and destination will be considered as es plus di. Now whenever this instruction is executed, then it copies the content which is pointed by ds plus si into es plus di. Okay, now after this copying operation, now it increments or decrements this si and di by 1 or 2. Now here increment or decrement depends on direction flag, and 1 or 2 depends on whether you are using this move SB format or else SW format. SB is nothing but byte wise, SW is nothing but word wise. Okay, and compare as, which performs, now actually we have seen what is this comparison operation, which performs a subtraction between the destination and a source. Now here it does the same. Okay, that is subtraction between the destination and the source, and the result will not be stored inside this or inside the source operand. Okay, now after performing this comparison operation, it decrements or increments this si and di by 1 or 2. Again, this depends on the direction flag as well as on this instruction format. Okay, and the result would not be stored in either of these memory locations, but it would be affecting the flags. Now we have scanf, which is mainly used for searching an element. Okay, now here the search element must be stored inside the AX register. Now what happens here is, whenever this instruction is executed, now the content which is pointed by the destination, okay, will be subtracted from the AX register. Okay, after that di will be incremented or decremented by 1 or 2, and we have load s, which is going to load the data from the source to the register. Okay, source is nothing but the location which is pointed by ds and si. The data will be loaded into AX or AL, and this SI gets incremented by 1 or 2 or decremented by 1 or 2. STOS, which is nothing but store string. Okay, now here the content of AL or AX will be copied into the destination, which is nothing but ES plus DI. Again it is similar, plus or minus 1 or 2 will be added to this DI. Now we have branch instructions. Now these branch instructions are again of 5 types, as you can see here: conditional jumps, unconditional jumps, iterations, call instructions, and then a return instruction. Now, why do we use what is this branch instruction? Branch instructions are mainly used for transferring the control from one place to the other place, or from one location to the other location. Okay, now let us see how to use these branch instructions. Now before that, let us see what is this subroutine. Okay, subroutine is a program which performs a task. Okay, now how do we call a subroutine? Subroutine or function or a routine, all are same. Okay, will be used for performing a specific task. Now how do we call a subroutine? So subroutine is called by using one instruction. So whenever the subroutine is called, then the control will be transferred to this first instruction of the subroutine, and then it executes this subroutine. And after executing the subroutine, now after executing completely the subroutine, now the control will again be transferred to the main program, where it is going to start the execution or resume the execution of the main program. Okay, now the same thing happens here, as we have called the subroutine A. So here first instruction as well as all the instructions inside this subroutine A will be executed, and after executing one last instruction, this control will be transferred to the next instruction in the main. Okay, from where it has to start, the same location. Okay, from where it has to start. Now what is a subroutine? It's a program which is used for implementing a task. Now how do we call a subroutine from the main program? So by using one instruction, that is a call instruction, we call the subroutine, or we call the function. Okay, now what happens whenever a subroutine is called? Now initially the content of CS and IP will be loaded onto the stack, and then the control will be transferred to the subroutine. Now here, after completely executing the subroutine, now the control should be returned back to the main. So for that we'll be using one more instruction, that is RET instruction, which returns the control from the subroutine to the main program. Okay, and while returning it again, retrieves the data from the stack, and that is stored inside this CS and IP. Now that address is called as return address. Okay, as you can see some examples, call 1234. Now it will transfer the control to this 1234 location. Call BX, it will transfer the control to the location under this BX. Okay, it means BX will be holding some value. Now that will be treated as an address. Now call instruction, which is a subroutine call. So call and operand. Okay, now the control will be transferred to the specified operand. Now here the operand might be near procedure, far procedure, within a segment, or within the segments. Okay, it means intra segment. Intra segment is near proc, inter segment is far proc, and then memory pointer, that is 16-bit address, and register pointer, which is again a 16-bit address, and then memory pointer 32-bit address. Now return, which is mainly used for transferring the control from the function or subroutine to the main program. Okay, now here the operand might be none. Directly we can write RET, or else we can also specify a 16-bit displacement. Now loop instructions, these instructions are mainly used for repeating a set of instructions, or executing a set of instructions repeatedly until the condition is satisfied. Okay, let us see what are those loop instructions. So loop and a label. Now this instruction will be executing a set of instructions under this loop instruction until the CX becomes 0. Okay, so here CX gets decremented by 1 for every loop instruction, or for every execution of the loop, CX gets decremented by 1. Now loop E or loop Z. Now set of instructions are executed until CX becomes 0, along with ZF should be 1 always. Okay, and then a loop NE or loop NZ. Now here again the same thing, it will execute set of instructions until CX becomes 0 and ZF should be 0 every time. Now let us see unconditional jump instructions. So without executing or without checking any condition, we can transfer the control from one location to the other location. As you can see here, without checking any condition, jump, we are transferring the control to a memory location, okay, which is specified as AE. Okay, so that is what is called as unconditional jump. Okay, jump and a operand. So unconditional jump can be of near jump or else a far jump. Near jump is nothing but intra segment, that is within the segment, and if you want to transfer the control between one code segment to the other code segment, or from one segment to the other segment, then you have to use this inter segment jump. Okay, so is limited to the address within the current segment. It is achieved by modifying value in IP, and permits jumps from one code segment to another. It is achieved by modifying CS and IP. Now conditional jump, it will check one particular condition here, and then if that condition is true, then only the control will be transferred to the specific location. If condition is false, then the next instruction after this conditional jump will be executed. Okay, now here the mnemonic would be JCC and meaning is conditional jump. Format is, that is syntax, the jump instruction along with the operand, and then operation, if condition is true, jumps to the address specified by the operand, otherwise the next instruction is executed. So none of the flags are affected. Let us see some of the instructions which comes under these conditional jumps. Jump if above. So here it checks these two flags, that is CF and a ZF flag, both should be 0. And jump if below, or jump if above or equal, and then jump if below or equal, JC, jump if carry, and JC exit, which is nothing but jump if CX is 0. Okay, so jump if equal, and then jump if greater, So these all instructions will be performing the condition checking on these flags. Okay, if those conditions are satisfied, then only transfer the control to the specified location. Okay, now jumps based on some single flag. Jump if 0, so if 0 flag is 1, then only it transfers the control. Jump if non-zero, if 0 flag is 0, then it jumps to the location. Jump if sign flag, jump if no sign, jump if carry, jump if no carry, jump if parity. If there is a parity, that is if parity bit is set to 1, then the control will be transferred to the specific location. And jump if no parity, again the same thing. Now jump if 0, jump if equal also mean same, so both are same. And jump if non-zero and jump if non-equal are again same. Jump if carry and jump if borrow is again same. And jump if no carry and jump if above or equal, and J and B, all these are same. Okay, as you can see, some of these same instructions or instructions which would be performing the similar kind of operation. Now we have the last kind of instructions, that is machine control instructions. Now if this halt instruction is executed, then the processor enters into an idle state which will not do anything. It will not do anything until interrupt signal is given through INTR pin, or else interrupt signal is given through NMI pin, or else a reset input. Okay, so when this instruction is executed, then the processor will be entering into the halt state, and it will come out of this halt state only through the hardware interrupt signal, that is through INTR, or else through NMI, or else through reset input. And no operation is the instruction which will make, or which does not do any operation until 3 clock cycles. And wait instruction, now the CPU will do nothing, that is it will not do anything. Okay, and it will come out of this wait when a test pin of 8086 becomes low, or an interrupt signal is received on INTR or NMI. And we have a last instruction, that is lock, under this machine control instruction. Now it is mainly used in case of multi-processor communication. If one processor is using the system bus, now while using the system bus, it wants to avoid the other processor to use the system bus at the same time, then it would be using this lock instruction. It would lock the system bus to the specific master until the transaction completes. Okay, thank you.